Well, that'll work, I guess. Any questions over the remaining stuff on the chi-square goodness of fit test? Everybody got that down, Pat? Where did we leave off on Friday? Oh, we did it. Yeah, we did the project Friday. That's right. And so I got everybody's project, right? Okay. And you were the ones that were missing a person, right? Your group? Yeah, and that was Courtney, and she's out for a little while, and so she's going to do it on her own, so you don't have to worry about that. Okay. So we did, last time we talked, other than the project, we were doing the chi-square goodness of fit test. You had some homework over that. And you had homework in stats or launch pad, right? Have you guys got that done?
I almost forgot about it.
I think it's due tonight,
Yeah.
right?
Which one was it?
It's section 9.2.
Okay.
It's in Launchpad. But I don't know if you're having issues like you had the last time or not, but let me know if you do.
The last question was weird. It's weird how it's worded, but I got it right, so I don't care.
So today we start linear regression. Chapter 10 is only a couple sections long and it introduces topics in linear regression, and then chapter 11 will move to multiple regression. Okay, and the only difference is multiple regression, you have multiple x variables in the model. Now, with the exception of Taylor, who's had regression already, he got out of order on classes, so you just have to keep quiet on all this stuff and don't spoil the fun for everybody. You'll have seen this before, but most of you coming out of MA343 know what regression is. You know how to make your calculator fit a regression line. But we need to now learn kind of a little bit of the theory behind a linear regression model, and how do we do inference about a regression model. Right? And how do we make predictions from it and make confidence intervals around those predictions. We didn't do that stuff in MA343, maybe just a little bit. Okay, so I thought what I would start with, I'm going to look at their PowerPoint from the author. And as I go through this, I'm going to stop, flip back over, do some stuff with some real data, come back, so we'll flip around. These formulas and things that you're going to get in this PowerPoint, I will come out of here and reinforce them on the board on ink. But if you get panicked because you're not getting them all down, guess what? They're in the book. And I can post this PowerPoint presentation for you. It's a good summary of the chapter. So when we talk about linear regression, we're talking about two variables, an x variable and a y variable, that are associated, or at least we want to see if they're associated, right? But they're both quantitative variables. So it's association between quantitative variables. For example, if I collect an explanatory variable as the number of hours that you spend studying for your first test in here, and the response variable is, what do you think?
Grade.
Your grade on that test. Hopefully there's an association there. The more time you spend studying, the better your grade is. Well, the first thing you do to look for an association is often a scatter plot. So what does that term mean, scatter plot?
Graph of lots of points, just showing you that.
Okay.
Graphing x and y.
X versus Y.
Oh, I know what I need to do. I need to flip. I just realized I opened that PowerPoint while I was remoted over to the WooStat server, so it's not going to be quite as efficient, but we'll make do. So a scatter plot not that. You have an x variable and a y variable. And remember x for explanatory. So you're going to use the value of the x variable to try to predict what value you would expect for the y variable. Now the example I'm going to show you comes out of my MA343 data. So a lot of you will have seen this before, so it should be familiar. My x variable is going to be shoe size. And the y variable is going to be height. Do you think there would be a relationship between somebody's shoe size and their height? Yes. And people with small shoe sizes you would expect to be shorter. People with large shoe sizes you would expect to be taller. Right? So you do a scatter plot. If you see a linear trend, like we just described, it should look something like that. Notice as x gets bigger, y gets bigger. So that's a positive association. So this particular picture is a positive linear trend. Okay? Now we fit a line to this data using what's called the least squares method. Some of you are looking at me like, what are you talking about? Others are like, oh, I don't remember this. Does anybody remember what least squares refers to?
Line of best fit.
Okay, it is the line of best fit. And why is it called a least squares line? Minimizes the residuals, but where's the squares come from? It minimizes the squares of the residuals. All right? So what's a residual? Okay, it's the distance between the point and a line. I guess I'll just stay with black marker. But that vertical distance from the line to a point is called the residual. You can also refer to it as error. Think of predicting, using the x variable to predict the y variable. The line predicts that the y variable would be there at the x I just drew. But the actual value is up here. So the residual is the difference between the observed value and the predicted value. So it's equal to y minus y hat. So y hat is our notation for the predicted value. So the equation of the line is y hat equal beta 0 plus beta 1 times x. Wait, that's not what you did in MA343. It looks similar to this though, remember? What does your calculator use? Instead of beta 0 and beta 1, it uses A and B, right? And I had you do one of these on that MA340 worksheet, right? So the calculator calls this A and B. And remember the discussion we had back then when we were reviewing, we talked about intercept and slope, right? Which one of those is slope? Okay, the beta 1. When do I use Greek letters and when do I use non-Greek letters?
Greek is population.
Okay, Greek letters are population parameters. So the theory behind this is that if you measure the shoe size of every adult, let's say in the United States, and then measure the height of those same adults, do a scatter plot, fit the line of best fit, there will be a slope for that line. So the slope you would get if you plotted every subject in the entire population, that's beta 1. Right? Of course, you can never do that. You can't measure everybody's shoe size and everybody's height in the whole population. So it's unobservable. You'll never know the true value of beta 1 or the true value of beta 0. So what is beta 0? What's the interpretation of that?
If somebody has a 0 shoe size, what their height would be.
Okay? That's the predicted height of somebody with a shoe size of 0, right? The y-intercept, where it crosses the y-axis. Now I drew my scatter plot here without labeling anything on the x-axis, but that beta 0 would be the height of the line whenever you cross 0. It may not be accurate here. Does it make sense in this case to extrapolate the line back to somebody with a shoe size of 0? No. Why not?
Because they're not born. They don't have feet.
Yeah, I don't even think there is a shoe size of 0. There is no such shoe. So it doesn't always make sense. The interpretation of the intercept doesn't always make biologic sense, or whatever your field of study is in this particular data set. It may not make sense, but that's what it's interpreted as. Well, let me go back to here, and I like being able to do all this with my finger. There's some assumptions that have to be met in order for a linear regression analysis to be valid. So this is combining the shoe sizes and heights for my entire data set across all my semesters. So there's just shy of 10,000 observations being plotted right there. You're supposed to go. Now, there's an awful lot of repeats. So this looks like a single plus sign, but there may be 25 points right there, right? Because shoe sizes are discrete, and so are heights the way they were measured. There's a few, but it's very rare that somebody said, oh, I'm 69.5 inches tall. They just round to the nearest hole. So there's a lot of overlap. There's a couple of oddities in here. I don't know if you can see them. Does anybody see?
Yeah, like between 8 and 9.
Yeah, right there. See that point? Somebody had a data entry error on their shoe size and entered 8.25. And there's another one there that's just off a little bit. But for the most part, they're in nice vertical lines. Okay. Now, one of the assumptions that has to be met in order for linear regression to be valid is that, well, let me back up. Think about taking each shoe size as a subgroup of the population. Okay? So, let me come over here. Each shoe size as a subpopulation of people with that size. Okay? This thing to turn. For the linear regression line to be considered valid, then we have to make some assumptions about those subpopulations. Okay? First thing is that all individuals, now I keep talking about people because I'm doing shoe size and height, but it doesn't, whatever it is you're studying, it might be, you know, tubes of toothpaste or whatever, but all individuals are independent. What does that mean to say they're independent? Okay? The results of one don't affect the results of another. Knowing something about one point doesn't give you any information about where another point is likely to be. So if I come back over here to the scatter plot, this point has to be a person who's completely independent of any other point in there. Now that can be violated if somehow you have like a time scale and you're measuring the same individual across time. Right? Like the value of a stock portfolio across time for the same individual, those would not be independent observations. So if you have dependence, then you use different methods. Least squares regression is not valid. You use different methods called time series analysis. Ooh, that's another class. Okay, so all of those individuals have to be independent. I'm going to go ahead and use this. Where I'm at. There it is. Conditions for regression inference. Right, so said, is this big enough to really read? I'll copy them over there, but for any fixed value of x, the response variable y varies according to a normal distribution. Okay, so that's the next requirement. For any value of x, fixed value of x, the response variable varies around the line according to a normal distribution. Y given x, remember this vertical bar means given, so y conditional upon that value of x is normally distributed. What the heck does that mean? Normally distributed. What's a normal distribution?
On both sides.
Okay, it's symmetric and bell-shaped. So basically what it says, for any value of y, or of x, you've got a subpopulation of individuals that have that particular shoe size. If you make a histogram out of the heights of all the people with a size 9 shoe, you should see a bell-shaped symmetric distribution. Okay, so let's go look at that. What I've done next, here's my scatter plot with all 10,000 observations on it. This is probably too small to read, but it says shoe size equal 5. Now, shoe sizes in this data set went clear down to 3, but I had so few subjects until I got to shoe size of 5 that it doesn't make a nice histogram. So I'm only showing you the ones that had enough data to be meaningful. Does it look bell-shaped and symmetric?
Yeah.
So what we're saying here is the peak of this normal distribution, which is at about 61 inches, on average, somebody with a shoe size of 5 is 61 inches tall. But it varies a little around that. It should vary according to a normal distribution. Okay? So let's keep paging down on this. In fact, let me make this full screen, and I'll use the button over here. So there is, I can tap it, can't I? I keep forgetting this is touchscreen. Here's shoe size 5.5. Here's shoe size 6. 6.5. 7. What do you notice is happening?
It's shifting right.
It's shifting to the right, but it seems to be pretty bell-shaped and symmetric each time. All right. 9, 9.5, 10, 10 and a half. Ooh, there was a real outlier. There's still an outlier down here. There's a few bad data points in this data set. Here's somebody who's 58 inches tall but has a size 11 shoe. 58 inches tall is, how tall is that? 60 inches tall is 5 foot.
So, geez, 4'8".
So 4'10".
Yeah, 10.
4'10", but a size 11 shoe. Right? Well, probably that's supposed to be a 68, but it's too late now to go back and recapture, so I've just left it in there. But ignoring the outliers, it looks pretty bell-shaped and symmetric. There's size 11 and a half, 12, 12 and a half, 13, 13 and a half. Now I'm starting to get pretty sparse on data. It's size 13 and a half is a pretty darn big shoe. 14, 15. There was no 14 and a half, or at least not enough to put in here. I think, nope, yeah, that was it. So let me go back up, and I'm gonna do it faster now. Let me see if I can make this thing stay on the screen. Nope, it goes too high. I need somebody to come hold it while I. How about that? Yeah, there we go. So I'm going to go back to the beginning. Now I want you to notice something different. Notice how it's shifting over, right? So as I go down quickly, you see that the graph is moving. How does it move? Well, this picture shows the mean of each of those histograms, where the peak was, as a function of the shoe size. What do you notice? Not just that it increases, but it increases in what pattern? Linear pattern. It's a line. Now down here at size 3 shoe, there was probably only 2 or 3 observations in the, so it's not reliable. I should pull that one out. There's an odd one there. I'm not sure why. I haven't investigated. And a little bit, and then up here at size 19 and 20 shoes, it gets really sparse. So there's only a couple of people. There is one person in the data with a size 22 shoe who was 91 inches tall. That's 7'7". But notice that if I ignore this kind of tailing off here and bring that line, they're pretty much where you would expect. But so without that, in the main part of the data, it's a very linear relationship. Okay? So we've gotten several things that have to be true for linear regression to be true. They have to be normally distributed at any value of x. We saw that, right? And then the mean value of y for any x. And we can denote that several ways, but we'll do it the mean value of y given x. Now I'm using notation a little bit different than what they have in the book. I want to reinforce this idea of a conditional distribution. Conditioning on your shoe size. What's the average height? So the average height of everybody who has a size 9. Then the average height, those are related, or they are a function of shoe size. In fact, it's a linear function. Hey, that looks just like that thing I wrote on the board a while ago where I had y hat. Right? Well, this is saying the mean of all of the y's for a given x follow a linear function of x. If they don't follow a linear function, then fitting a linear regression line wouldn't make much sense, would it? If you do that plot the means for each value of x, and it doesn't look like it follows a line, then use some other way to analyze the data, because the linear regression isn't going to be appropriate. Now, the fourth one, let me go back and page through these real fast again. Concentrate this time on the spread of the distribution. In other words, yeah, it's normally distributed, But if some have a lot of variability and some don't have hardly any variability, that's not good. We need them to have what we call equal variances at each x. So the distribution of y given x should not be a function of x. It should be constant. So pay attention to it makes more sense to look at the black superimposed normal distribution each time I hit page down. That's the best fitting normal distribution for that particular histogram. And just see, does it seem to get wider or skinnier, or is it staying fairly constant? Do you have a question?
You haven't swung over there yet.
Oh, yeah, that's right. Keep me honest on that. All right, so now watch it. What do you think about the amount of variability in heights around the shoe sizes?
Getting wider as you get taller, or it's getting wider as the height.
Well, it's not
It changes in the middle in places.
There's a few of them that it changes a little bit, but for the most part, it's pretty constant, isn't it? If I had one of you go up there and hold your fingers and move your fingers along, you wouldn't be having to move them out too much, right? This is known as the constant variance assumption. So the variance of y, which is sigma squared of y given x, more Greek letters. Remember, sigma squared is variance, sigma is standard deviation. So if the variance is constant, so is the standard deviation. So you can say it either way. But the variance of y for each given value of x is equal to sigma squared y, and then note no x. It's not a function of x. It's constant. It's a constant variance. So I'll put that over here. Constant variance. Okay? So for each value of x, y has to be normally distributed. It has to have a mean for a given x that is a linear function of x. And the variance has to stay constant. And they have to be independent. So those are the conditions that have to be met for linear regression to be considered valid. For us to be able to make valid inference about the slope and the intercept and predicted values that we make from the regression line.
Did you give us an extra one in regression?
What's that?
Did you give us 5 in regression? I thought there was one that our book doesn't touch on that you told us. It may not matter, that's why I'm just curious.
No, this book doesn't do that. It's the I'm not even remembering for sure which one it is that this book doesn't do. But where did I put the? Oh, yeah, it's on the wrong. This one. So look at the way the book describes it. For any fixed value of x, the response variable y is normally distributed. The mean response, mu of y, they don't put the slash or the vertical line x, but the mean of y has a straight line relationship with x. Okay? That's the number 3 that I have over there. The slope and intercept are unknown parameters. Well, that's not a condition that has to be made. That's just always going to be true. They are unknown parameters in the whole population. Then the standard deviation of y, call it sigma, is the same for all values of x. The value of sigma is also unknown. It's a Greek letter. It's a parameter of the population. There's no way to know that value. You have to estimate it from your data. So I like this picture that they have from the book, and this picture is in your book. Notice what it has here. I haven't yet figured out a way to do it, but I could take my histograms of each of the shoe sizes if I could kind of tilt it on its side and make a line of those dots that I showed you, and then put the histogram around it, that's what this is a picture of. It's saying for whatever value of x, you get a certain amount of variability around the line, but it has equal width all the way. Each one of these is the same width. And their means, the vertical line in the middle, follows straight on that line. So it's combining several of those things all in one. So now he says data, right? Your data points that you have can be summed up, or can be thought of as the sum of two things: the fit plus error. The fit is the line part of it, beta 0 plus beta 1 times x, plus some error. What's that error called? Yeah, it's an epsilon, but we called it, what's the word we used? Residual. So these epsilon sub i's are the residuals. So those epsilons have to be independent. Knowing the prediction error for one individual does not give you information about the prediction error of another individual. Okay. Now, this is different, but means really the same thing as this. So number 2, I have the y's are normally distributed for each value of x. But that's equivalent to saying the epsilon i's have a mean of 0. Why is that equivalent? Well, look at this line. What are the residuals? Epsilon sub I. And sub I, just the subscript simply means for the ith individual. Right? So person 1000, their residual is equal to the observed value minus the predicted value, right? So the predicted value is this mu. So why does these two things being true imply that the mean of the epsilons is 0?
Because you're going to have positive and negative residuals.
Okay, you're going to have positive and negative residuals around the line. That's the line, right? For a given value of x, this value of mu is where the line goes. Right? So you've got, say for a size 4 and a size 5 shoe, you've got a line going through there. This is mu of y given 4. This is mu of y given 5. So the residual is yi minus mu y given x. I should put a subscript on that x. So for the x, for the ith person, their residual is their actual y value minus the predicted y value from the line. So if this is true, then this is beta 0 plus beta 1 xi. So the mean of that, the mean of these y's, if I want to know the mean of the epsilons, I take the mean of every piece here. The mean of these y's is what? What's the mean of the y's? It says right here, the mean of the y's for that value of x is that thing. So this is mu, is beta 0 plus beta 1 xi. This is the same thing, so the difference is 0. So I only get to put that in for yi when I'm saying, okay, I want the mean of all of those, right? So for each individual, it's their observed value minus the mean of all of them. Well, then now if I average, this is the mean of all the y's, but this is also the mean of all the y's at that value of x. So they add out to 0. So the epsilons have, the book does not use this notation. Where's my eraser? I had one, didn't I?
There's one over here on this board.
I guess I haven't used one yet. So I give this in my regression class. The book doesn't really use this notation, but you can sum that all up about all of these by saying the epsilon i's are IID in 0 sigma squared sub epsilon. Okay, whoa, what? IID stands for independent, ooh, there's that one, identically distributed. Okay, so they all have the same distribution. And this says what that distribution is. So what do you think N stands for? Normal. Right? So the epsilon i's are independent and identically distributed as normal with a mean of 0. So the residuals mean 0 around the line with constant variance. There's no I subscript and there's no X. No dependence on X. It's just a constant. So you get your constant variance, you get your normally distributed, you get all of them independent, all out of this statement. The thing that this doesn't say is that the means at any x have to be linearly, is that a word? Distributed. Or linear function of x. But if they're not a linear function of x, then you're not going to get this mean 0. Questions on that?
So if n means normal, what does the 0, sigma mean again in words?
The 0 is mean, right? So that's standard notation in statistics. That this means normal distribution, and this is the mean of that normal distribution, and this is the variance of that normal distribution. Okay, so normal, mean, 0, variance, sigma squared sub epsilon.
And in this case, the sigma squared sub epsilon is showing constant variance.
Right. So down here I wrote it as sigma squared sub y, but that's really why that's bad notation. Sigma squared of y conditional upon x needs to be constant and not depend on x. The value of it is not a function of x, but the notation doesn't work. And in the book, he just uses sigma squared y. But here's why that bothers me. Let me come back to here. I need to figure out how to get, there we go. Back to this. This is why that bothers me. This is my y variable, right? So what's sigma squared sub y? What's the variance of y? Well, it's not that marker. There's my minimum value of y. Here's my maximum value of y. So all of that goes into computing the variance of y. If I ignore x completely, how much variability is there in people's heights? There's a lot.
A lot.
But if I now think of variability around the line, I'm conditioning on x. Right? So I take out, well, think of it this way. I'm going to do a magic trick. You ready? I'm going to grab this line by the ends and I'm going to pull it up off the board. And then I'm going to tilt it down and put it onto the x-axis. Did you see that? And all the points come with it. So now what do I have? I've got points that look to be about that much spread around the line. This is known as a residual plot. So it's basically doing exactly what I said. Pick it up and set it down. Now you've made your line horizontal and you're looking at spread. So this is the variance of the residuals. That needs to stay constant. It can't get bigger as x gets bigger or smaller as x gets smaller. It needs to stay a constant band around that line. The same thing is true here, but it's harder to see when it's sloping up. That's why we do residual plots. So taking that conditioning on x off of here, I don't really like that notation because then it implies the variance of the y's ignoring x. But he makes the point using this sigma squared y that it needs to be constant for all x's. So the text is correct. It's just the notation is a little cumbersome. Okay? So, how do we find that line of best fit? How do we compute the slope that fits the best? How do we compute the intercept that fits the best?
Put the data in your calculator. Do it then, right?
Maybe somebody would be smart enough to say something like that. Let's do this. What I have here is a yeah, that's what I want. And let me see if I can scroll it. Still fit okay. So if you can see these numbers, I've got an x variable and a y variable, x1 and y4 for the first observation. I've got 5 observations, and then 4, 12, 7, 16, 10, 26, and so on. Right? On the scatter plot, you can see those points are these blue diamonds. So, can I scroll like this? Yeah, there we go. My first attempt at a regression line is a horizontal line. Now it's horizontal if you don't believe that y is related to x. Right? So a slope of 0 would say, well, there's no relationship. Y doesn't change as x changes. It stays horizontal. Now, remember when we said what least squares means? We call it least squares because we're going to take the sum of the squared residuals. And Corey told us a while ago why we have to square them. You didn't know you were saying it, but do you remember what you said?
Because you're going to have negative and positive.
You're going to have negatives and you're going to have positives. So if you just sum the residuals, they will always sum to 0. So we need to square them, then sum them up. So we want the sum of the squared residuals to be as small as possible, the least squares. Okay? So right now I have a slope of 0 and an intercept of 16, and I've got a sum of squared errors, SSE, for sum of squared residuals. Remember, residual and error, same thing. So this is standard notation in statistics that SSE means sum of squared errors, sum of squared residuals. Okay? So if I use a slope of 0 and an intercept of 16 as my line, I can compute y hat. Now what's y hat again?
The distance from the line.
No. It's, what'd you say? No. The residual is y minus y hat. What is y hat?
Predicted value.
The predicted value. It's it's the number you get back when you plug x into the equation. So when I plug x into this equation, all right, so let's start with x equal 1. Plug it in, what do you get? You get 16, because you take 0 times x, add 16, you get 16. In fact, you get 16 for all the y hats. The residual is y minus y hat, so that's a negative 12, a negative 4, 0, and so on. Square them, you get these numbers, sum them up, you get 381. Now, obviously, you could probably do better. So give me a different slope than 0 that might do better. Remember, these blue points are the observed data. And I'm going to make this just a little bit smaller.
Try with
There we go. Okay, so I got a point here. So what do you think for a slope?
that. 1.
A slope of 1? Okay. And what about an intercept? I used an intercept of 16 before, but if I have a slope of 1 and it's coming down through, what do you think the intercept would be? 3? Okay. Does that work? Nope. So let's change this number to, I got to type it, I guess.
If
To
you
1.
click the left side, a keyboard comes out. The little arrow thing.
Yeah, there's a gray arrow on the left side of the screen.
Yeah.
Now we're trying to
No, tell me again now that I'm over here. There's a,
On the left side, right where you're.
oh, this thing?
Yeah, I think it's. if you
Yeah,
type it-
and Leanna was telling us that one doesn't work very well, right? There's another way to get a keyboard, and I don't remember how, but anyway, I'll just go over there. Let me scroll back. Did it work?
So,
It didn't work real well. The intercept's not too bad, right? In fact, you nailed that first point. Look at the first point. Y hat was 4, Y was 4. You got a 0 residual. But when you sum them up, now you got SSE of 351. What was it before?
380.
381. It got better. We're trying to minimize it, right? Give me another slope. Give me a better attempt.
1.75.
1.75, okay? This line doesn't look steep enough to you, right? So you're going to make it steeper. 1.75. I'm going to leave the other one at 3,
sure.
okay? And I'm going to try to just kind of leave it in between, but we care about this number. We're trying to make it get as small as possible. So change the slope to 1.75. Boy, we got a huge drop in the sum of squared errors. It went from 351 to 36.9. Much better. Can we do any better than that?
Yeah.
What does the intercept look like now?
Intercept's still not too bad, is it? But the line needs to be just a little bit steeper yet, doesn't it? 2? Okay. Let's make it 2. Sum of squares is 16. You think you can do any better than that?
I don't think so, because you probably planned it to be a nice round number.
True. That is the smallest you can get. That is the least squares line. Now the sum of the squared residuals is as small as it can get. You can't beat 16. You want me to prove it to you?
Sure.
Sure.
Okay, good. I was hoping you'd say yes. To do that, I need to run the regression. And I went too far. In Excel, you can run a linear regression pretty easily, and I've done that here. The top part of this is called the ANOVA table. That's short for analysis of variance, right? We'll talk more about that in the second section of chapter 10. But for now, look at the intercept and the slope that it fit. Saying that we finally zeroed in on. And notice this number. In the ANOVA table, it has residual and then SS. What does SS stand for? Sum of squares. Sum of squared residual, 16. Since it's got an algorithm to find the absolute best fit, then you know you can't beat that. And that's what we hit over there was 16. Okay? All right, so we'll quit there. Next time we'll derive the equations for computing that slope. Instead of guessing at it, we'll figure out how it's computed.
Well, thanks.
You'll have homework